So, back in the days where people were just fighting for bread and surviving, trying to live to see the next day, that was the only soul or the sole purpose that humans was on the planet for. There stood this guy called Lucipitus, and then his student called Democritus. Now, what Lucipitus asked himself was that what is matter even made up of? Right? So then he took something, an object, whatever it is, he took it, right? If it's like this size, he cut it into half, right? And then it goes into this size, right? The other half. He take this half and then cut it into half. And then he get this size and cut it into half and cut it into half and cut it into half. You get what I mean? So what he figured out was that if you cut anything into half and then cut that half into more half all the way, you're gonna certainly get to a point where you cannot cut that item anymore. And no matter what you do, you cannot cut it. So then he said that matter is made up of tiny particles that cannot be cut, right? Or that cannot be destroyed. Now, he said that around 450 BCE, right? Around 450 BCE. BCE stands for before common time, right? Or before common era, right? So a couple of years after, around 337 BCE, during those times, they counted the days back. It's not like today that we counted 2026 to 2027. They counted it back. So from 450 BCE, it went back to like 436 BCE. His student, right, called Democritus, and by the way, that is not where the term democracy came from, right? His student called Democritus, what he said was that, okay, my boss said that matter is made up of tiny indivisible particles, right? Then I will call that particles atomos. So he coined the word for an atom by calling it atomos. Right now, atomos is a Greek word meaning, depending on the version of a textbook that you read, it could mean indestructible. It could also mean uncuttable. It could mean unchangeable, right? So he coined the word atomos. And then he said he made a couple of postulates with this atomos word that he coined. The first one that he said was that matter is made up of tiny indivisible particles called atomos, which his boss has already said it. So let's write it over here. Matter is made up of tiny indivisible particles called atomos. So Democritus said this, right? But he did not stop there. He went on to make a few more postulates. The second postulate that he said was that matter, it was the atom of different matter, right, was made up of different, like atoms of different matters were different, right? So a matter, like atoms that is inside like a chair was different from the atoms that was inside of the shield that they might have used to work, right? So he said that atoms of different matters are different in shape and sizes. So this is the second postulate that he made. right? And then when he made this postulate, he did not stop there. He went on to say that the atoms of iron that we use today, iron, Fe, iron, right, were made up of hook and locks. So he said that the iron atom will look like something like this, like a chain, like a hook and then a lock. That is why it is so strong. That was what he proposed it to be. So the hook will go into the lock and then it will be super strong. You cannot break it. He also said that the matter of salt was spiky, right? Like if you draw a salt grain here, he said the matter was spiky, right? Why did he say that the matter of salt was spiky, right? That is because when he ate salt, he burned his mouth, right? He has some type of oral disease. So when he ate salt, it burned his mouth. And because of that, he said matter of the atoms of salt is spiky. Now, when he said that, around those same time, like around that 437 BCE, around this era, there was one philosopher. Mind you, these two were not scientists. They were philosophers, right? They were just natural observers, not scientists, right? There was one another philosopher called Aristotle, right? Let me put it here. One other one called Aristotle, right? Now, Aristotle said that he did not believe what these two are saying, Leucippus and then Democritus. Why did he say that he did not believe it? He said that matter, Aristotle also made his postulate that matter, right, is made up of 4 fundamental elements, right? What are the fundamental elements? So let's write here. Matter is made up of 4 fundamental elements. What are they? The fundamental element was, and you're gonna like this. He said there are air, water, fire, and then earth. Isn't it funny, right? That was what he said. The matter is made up of air, water, fire, and then earth, right? Now, you might ask yourself, why? But people did not believe these two. They believe him. They believe Aristotle. Why? Because he was popular and he has published book, was doing fine art at that time. He had the credentials to back his saying. These two did not. So these two never got the credit that they deserve until further down the line when scientists started looking into what matter really is, right? Now, one thing that I almost forgot, Democritus also made one postulate that atoms, right, the change of state of matter, why something would change from solid to liquid, was the rearrangement, right, of the atoms in the same element. Aristotle countered that argument by also saying that matter, like quantities, every matter is made up of a specific quantity of these things. It doesn't matter whether it's an element or a compound. It's just a specific quantity of these things. Now, that is what these people do way before the inventions, way before critical thinking started to start in, way before time itself. So if anything, let's give thanks to these two for observing them. Now, way back down the line, mind you, this is way back down the line. In 1803, right? In 1803, an English scientist by the name John Dalton, right? decided to look at matter. So way before Leucippus and then Democritus came and then made their postulate, and Aristotle also made his postulate, but people did not believe these two, even though they were the true, somewhat true. But then they believed Aristotle because Aristotle had the fame and the credentials to back up on it. Now in 1803, a scientist, he was an English scientist. He was a physicist, a chemist, and a meteorologist. Meteorologist, somebody that looks at weather patterns, right? He came to also observe matter, right? John Dalton is the person we was talking about. So when he came to observe matter, he made 5 postulates with his observations. And these postulates were not made out of thin air as these two, right? These postulates were backed by experiments. Because before him, there has been a previous play with matter, and then also there were scientists that have put forth some type of fundamental or foundational knowledge for him to build upon. So the first postulate that Dalton made, and do not forget this, was that all matter is made up of atoms, right? So all matter is made up of atoms. And then he said atoms are indestructible. So these things, like these 2 sentences, they are just one postulate. They are just the number 1 postulate. All matter is made up of atoms. Atoms are indestructible, right? That is the first postulate that he did made. Now we will come into how he came up with this conclusion. He didn't just copy and paste what Leucippus and then Democritus has already said, right? So the second postulate that he made was that all atoms of a given element are identical in shape and size. So what he says that all atoms in a given element are identical in shape and size. Now you might also see that isn't this like a version, like a knockout version of this? Like atoms of different matters are different in shape and size, right? But then we're gonna get into why he made this postulate. That the second postulate, all atoms in a given element are identical in shape and then in size. We're gonna get into how he made this postulate. So the third postulate that he made was that compounds, right, are formed in a combination of a fixed, like let me put it this way. Compounds are formed with in a combination. When you combine different elements, that is when compounds are formed, not the destruction of them. So let's go. There are compounds are formed from combination of different elements in fixed ratio. Let's rush to the fourth and then the fifth one so that we can just tackle them all together. Chemical reaction involves the rearrangement of atoms and not their destruction. And then the fifth postulate that he said, atoms of different element differ in shapes and sizes. So these are the five postulates that Mr. Dalton made. The number one postulate is atom. The number one postulate is that all matter is made up of atom. Atom is indestructible. Number two is all atoms in a given element are identical in shape and size. Number three are compounds are formed from combination of different elements in a fixed ratio. This is really important one because we're going to talk about it. And then he also said that chemical reactions involve the rearrangement of atoms and not their destruction. So he said atoms are never destroyed in chemical reaction because they already said here that atoms cannot be destroyed. So it is just rearranging of these atoms. And he said atoms of different elements differ in shapes and sizes. Right? Now, why did Mr. Dalton come up with this five postulates? Let's not forget that Mr. John Dalton here was a physicist and a meteorologist. So he was somebody that looked at the weather, right? And if you are someone that looks at the weather, you might have intrinsic knowledge about gases, right? So mostly he did experiments on gases, right? And then he figured that these are the postulates that a gas would follow, right? Because one, matter is made up of atoms. Atoms are indestructible. The reason why he said that was that anytime you have a gas in a tube, right, no matter the amount of pressure you put on it or the temperature you pass the gas through, at the end of the day, when you measure the quantity of the gas, whether it by its mass or by its amount of substance, which is the mole, it is always the same as the beginning of the experiment and the end of the experiment. So that is why he made this, that atoms can't be destroyed, because if they can be destroyed, then there should be some form of loss if you do an experiment with them, especially a harsh one. And then he said atoms in a given element are identical in shape and size. This was mostly because of how gases reacted, right? How different densities, or how gases have different densities, and some gas might float on top of each other. This gave the notion that atoms of the same element are identical, because there was no way possible that he was mixing a helium atom, a helium gas with an oxygen gas, or a chlorine gas with an oxygen gas without some type of separation, right? So this gave rise to this: atoms of different elements differ in shapes and sizes, right? Because if you can physically separate them, they might be different, right? So this one, the third postulate, that it says compounds are formed from combination of different elements in a fixed ratio. The reason why he came out with this postulate was because, as once again I said, he was a meteorologist, and then he always find out that carbon monoxide, right, would decompose to form carbon and then oxygen, right? Oxygen gas, right? But why he realized that anytime carbon monoxide decompose to form carbon and then oxygen gas, he realized that it is always 12 grams of carbon, right? And then 16 grams of oxygen, right? He also realized that, so these are not the moles, these are grams, right? So let me just put it here so you don't confuse it for moles. Let me write it with a different ink. 12 grams, 16 grams, right? And then he also realized that carbon dioxide, right, which was really close to carbon monoxide, carbon dioxide, which was close to CO2, which was close to carbon monoxide, also decomposed to form carbon dioxide plus oxygen. But then in this case, it was still 12 grams of carbon, but over here it was 32 grams of oxygen, right? So from these two data, right, he figured out that if you take oxygen here, right, the quantities that it combines to form either carbon dioxide or carbon monoxide, the quantitative ratio is always going to be 16 ish to 32, right? And 16 is 32 can be coined into 1 is to 2. He always said that for carbon dioxide too, it was going to be 12 is to 12, and that is 1 is to 1, right? So he said, that's why he said compounds are formed from combination of different elements. So different elements in a fixed ratio. So the ratio is always fixed. So for oxygen here, it's 1:2. For carbon dioxide here, it's still 1:1. So the ratios never change, no matter how many or how much he put in, no matter how much grams of different element that he put in, the ratio always remain the same. So that is why he came up with this postulate, right? But then the fourth postulate said that chemical reactions involve the rearrangement of atoms and not their destruction. We've already talked about this, because if you said that atoms are destroyed in a chemical reaction to form new atoms, then this postulate might be wrong, right? Because then you just said atoms can be destroyed. So that is the Dalton's 5 atomic postulate that was coined in 1903. Now let's go over it one more time. Number one, he said all matter is made up of atoms, and atoms are indestructible. Put that in mind. 2, atoms in a given element are identical in shape and size. 3, compounds are formed from a combination of different elements in fixed ratios. Compounds are, so this still holds true. When you combine compounds to form an element, they are always in a fixed ratio. Another way to remember this is balancing chemical equations, right? So whenever you trying to forget this postulate, the first thing that should come into your mind is, why do we balance chemical equations, right? And then it's because they are always in fixed ratios. So we're just trying to balance the ratios that they are combined to form such products or reactants. So when we move on, the fourth postulate is that chemical reaction involves the rearrangement of atoms and not their destruction. So chemical reaction involves the rearrangement of atoms and never their destruction. The fifth postulate, atoms of different elements differ in shapes and in sizes, right? Now, these are the postulates that Mr. Dalton made. But then there are some limitations to the postulate that we made. As we know of our studies in chemistry has progressed further, we've realized that there are limitations. Some of these do not hold true. And then we're going to go into that shortly. Let me clean this over here real quick. So let's do the limitations to the Dalton's theory. So let's do the limitation to Dalton. The first one that we could say is that he said matter is made up of atoms, right? He said matter is made up of atoms, which this part is correct. But then he went on to say atoms are indestructible. But from now, we know that atoms can be divided, right? So atoms can be divided into the subatomic particles. Into the subatomic particles. which today we know are the protons, the neutrons, and then electrons. Right. Even these can also be subdivided into, now we have quarks and whatever if you are doing in-depth quantum physics, but we will leave it here. We do not want to go into that rabbit hole. So that is the first one, right? Now the second one of the limitations was that not all atoms of the same element are the same in shape and size. Why? We now have isotopes, right? Isotopes are atoms of the same element that differs in neutron number, right? So because of that, you cannot say that all atoms of the same element are equal in shape and sizes. And because of the isotopes, this theory don't hold anymore, right? So two, the presence of isotopes will defy the second postulate. Right. Now, if anybody read a chemistry textbook, I know that you could read this and then read that, probably explained it better than I did, right? But then there is something that I want to draw your attention to over here in this postulate, right? When Dalton made these postulates, he didn't just leave them there, right? He came up with what the atom might be look like, or we could theoretically predict what he might think the atom might look like. So he would say, pick any element, gold, for instance, right? Its atom might look like this, right? Like this, where each circle is an atom on its own. But then the only difference is that each circle is just fixed. It can't be penetrated. Nothing can happen to each circle, right? So theoretically, that would be Dalton's atomic model. So let's move on from this one. I hope you all understood the Dalton's model. Now, right after Dalton, not right after, almost like 100 years later, right? A scientist by the name Joseph John Thomson in 1897, right, also went on to look into an atom, right? Now, before J.J. Thomson looked into an atom to see what was inside there, once again, scientists have put forth, right, some fundamental knowledge. They were working with matter, so they had to come into some type of an agreement, right? So you might ask yourself, where did J.J. Thomson even get a cathode ray from? Right, to go into his cathode ray experiment to discover the electron, because cathode rays was already being used. It was pioneered by earlier scientists. They knew that if you shine an electric beam on in a fluorescence tube, it glows, but they did not know why it glowed. So that was why Mr. Joseph John Thomson looked into it. So his idea was not to actually discover electrons. His idea was to, why does it glow when we shine electricity through a cathode ray tube that is also a fluorescence tube? Why do we have this glowing beam of light? And what is this glowing beam of light made up of? What is it actually? Right? So then gave birth to the infamous cathode ray experiment. So let me just write it here. The cathode ray experiment. Right. Now, the cathode ray experiment is one of the experiments that have been repeated over and over again, and it proves the same thing, right? If you are old enough, the TV with a big back, I'm not old enough, but I saw it from time to time. That TV with a big back, that they call it cathode ray TV. Is that tube. It's like a similar tube, but this time it was a vacuum because all the whatever was inside it had been vacuumed out. So J.J. Thomson, right, picked up a cathode ray, then passed electricity. See, there was even batteries. So you might ask yourself, where did he get a battery from, right? People were working. People had laid foundation, right? Faraday was playing with electricity and electrolysis before J.J. Thomson discovered electron. They knew they were doing electroplating before they knew what electron was. It's basically like learning how to fly and you don't even know why you walk or how you walk, right? So that is how it went. So J.J. Thomson picked the cathode ray tube, passed electricity onto it, and then the beam of light hit the other end of the fluorescence tube. So he got curious. What specifically is this beam of light made up of? Right? Now he went on to do some few experiments with this beam of light. At first, he connected electric field also here, right? And when he connected electric field here, this beam of light mysteriously bent away, right, from the middle line, and it bent up like this. It bent up towards the positive side of the electric plate, right? So then he got curious that this beam is attracted by electricity, because when he switched the flow of electricity, also when it bends towards wherever the positive thing is. Then he once again introduced a magnetic field, right? So let me take this electric field away from here, and then let me just put like a magnetic field over here. This it is the north south of the pole, and then the south end of the pole, right? When he did this too, the ray did what? Reacted to it. The ray also bended away from the normal also, right? So then he said that this ray right here is also affected by magnetic field. So one, cathode rays are affected by both electric and magnetic field, right? So since they are affected by both electric and magnetic field, how are they affected by it? So the cathode ray bends to the positive end, or the positive side of the electric field, right? Since it bended to the positive side of the electric field over here, they also knew that like poles attract, and they knew that like poles repels and unlike poles attract. So if a positive is being attracted to some charge, then that charge might be what? A negative charge. So then they came out that then the cathode rays might be negatively charged, right? Because they are negatively charged because it bends away from the negative side. It get repelled by the negative side of the electric field and get attracted by the positive side of the electric field. So once J.J. Thomson was done with this beautiful experiment, right? Now, he came up with his own atomic model, right? Let's come over here, clean John Dalton stuff away from here. So after J.J. Thomson in 1897 was done with his cathode ray experiment, he came up with this cool name, the plum pudding. Now, the plum pudding is a British food, right? It's a pudding with some type of bean embedded in it. So if you take, assuming this is your bowl of pudding, right, and then you have this bean embedded in it like this, right? This is how he envisioned the the atom to be. And the reason why he envisioned it to be was that he said the atom is a positive charge sphere with negative electrons embedded in it. The reason why he said it's a positive charge sphere was that even though when he shines electricity through the cathode ray tube, he gets a beam of light, and that beam of light reacted to both electric and magnetic field. Every atom that you pick is almost neutral. Like when you pick this thing, or any matter that you pick for that matter, if you pick this matter, it is neutral. It doesn't react to no charge or anything like that, right? On its own, sitting there, that is nothing, right? So why is it a neutral charge whilst it's just there? Then it might have like a positive counter effect that will counter this negative charge here, so that it will be neutral. That is why he said the entire atom is a positive sphere, right, with new electrons embedded in it. Now, if you are an American, think of this as why should I a muffin, right? A muffin with some raisins or with a blueberry muffin. Think of it as a blueberry muffin. Now, when you have a blueberry muffin like this, you have, let me see this. You have your blueberries embedded in the muffin, right? That is, so the entire muffin will be the matter or the atom in this point, and it's positive, and then the blueberries in it will be the electron having enough charge to counteract the positive charge of the whole thing, right? So then he called it the plum pudding model of the atom, and then we finalized it. So this became the first ever structure of an atom that we ever got from J.J. Thomson, the plum pudding. Now, the experiment went on to discover some other things, which we are not going to get fully details into it. The experiment went on to discover the charge of the electrons, what charge they carry. It went on to discover the mass of the electron. Why? How could he figure out the mass of the electron? It was by using something we call mass spectrometer. We're going to go on through it over the next chapter. So this experiment didn't only discover electrons. Electrons were just one of the things it discovered. And then they demarcated the negative charge to an electron. Now, negative. Like, you could ask yourself, did you just wake up and just coin up the word you are a negative charge? No, they did not. Scientists before that had already experienced charges. They know what charges were. They know attracting charges and they know repulsing charges, right? So they demarcated the attractive charge, which is positive. They called it positive because they started with I think the Greek or the Latin name called posere, which means to agreed upon. So they agreed upon to call it a positive charge. And then the negative charge, which is a repulsive force, they said they agreed to call it negare. Please, if you are white, don't be saying this word out loud, right? They call it negare, right? Negare, which means to deny. So that is where the word negative and then positive came from, right? It wasn't that it was a characteristic charge or whatever. It's because they agreed upon to call a certain thing something. You might also ask, what makes it positive or negative? Nothing. They just agreed upon it. They could wake up tomorrow and then be like, today positive is negative and negative is positive. And they're still going to do the same thing. A common example would be like, we all wake up today and decided that we're going to call on top of our roof a ceiling. If we wake up tomorrow and then we say that that is no longer called the ceiling, but rather the floor is the ceiling. Does the floor automatically becomes up? No, it doesn't. It's just a change of name. That is how positive and negative came to be. So we now have the plum padding model of the atom by J.J. Thomson, and that was timeline part 1. From Louis Seppitus, we went to Dalton, and then from Dalton, we went to J.J. Thomson, right? Joseph John Thomson. And then Joseph John Thomson gave us the what? The plum padding model of the atom. So that is the timeline part 1. Thank you very much for going through the timeline part 1 with me. Tomorrow or the next time I get a chance to shoot the second video, I'll shoot the part 2 of it, which is going to be tomorrow. And that will probably be the end of the timeline. We're just going to do 2 series onto it. Then we're going to jump into the more serious stuff. These are just the foundational or fundamental knowledge. Thank you. Please, if you enjoy what I'm doing and if you think it's going to help you, this is 2025. If you subscribe and then you like this video or you leave a comment section, it's going to help boost this channel so that your brothers and sisters and whoever is in this would benefit. Thank you very